for the average value of the function, we call the value of the function. This is the y value. This part is the y value, which is the function value, the f of x value. Your goal is to find the average of the value using the definite integral. We know the definite integral is the net area. So the definite integral is the net area from point A to point B. So then if you know the area or the net area and the area, the concept of finding the definite integral based on the sum of the area of the rectangles, the small rectangles, using the slice and sum technique. Okay, and from the area of the rectangle, we use the classic formula length times width, or the height times the width. Okay, the height times the width, and the width, based on the figure that we have here, the width is the delta x here, which is b minus a, the width, so b minus a. And we know the average, no, we know the area of the rectangle, or the area of the region bounded by the curve from point A to point B in the definite integral form from A to B of the function with respect to x. You know the area, you know the width, you're gonna find the height, and the height here we're gonna use as the average of the function value, or the f bar. You know quantity, you can solve for the missing one. So then the f bar, or the height, can be found by dividing the net area by the width. So that's why it come up with the formula 1 over b minus a multiplied by the definite integral from point A to point B of the function with respect to x, as a formula that you see in the box here. So the f bar is the notation for the average value of the function. From the figure, you see the rectangle. The area of the rectangle is the same as the area that's in the shaded region in green. Okay, so that's the concept of the average value of the function using the definite integral. Okay, now the first example that we went over, you'll go again, read the problem and make sure you understand or look at the key point what the problem asks you to find. This one, we're going to find the average value, which is the f bar. Yeah, this is the f bar of the function provided on a given interval. The interval provided is negative 2 to 2. That is from point A to point B. Your A is negative 2, your B is positive 2. You can draw the graph and indicate the average value. Last time we found the average value, and then I drew the picture to explain after that. So let's go backward this time. So if we draw the graph of this function, this is a parabola opens up with the translation by shifting upward 1 unit. Okay, the y-intercept is at 1, and the shape just a U-shaped graph or the parabola graph from negative 2 to positive 2. We know how to find the net area from negative 2 to positive 2. The goal of this one is to find the average function value. We call the y-axis or the vertical axis here. From the total area here, if we use it to find the average function value, the average function value would be somewhere between the value 1. So this part, so let me see. So this is the function value 1, which is the f at 0 equals 1. The maximum height, which is from the graph, that easy to calculate. So the function value at 2 would be 2 squared plus 1, or 5. So the average function value should be somewhere between 1 and 5. So between 1 and 5. Okay, so approximately somewhere over there. If I draw the rectangle using the red line here to show the height or the average height. So the area in red equals the area in blue or the original area from using the net area or the definite integral. So the idea is to find what is this point of the function or what is this f bar that make these two areas the same. Okay, so from the formula, the f bar or the average function value is 1 over the width which is b minus a, the b minus a or 2 minus negative 2 multiplied by the net area using the definite integral from negative 2 to positive 2 of the function x squared plus 1 with respect to x. And from the use of the odd even function, we know that x squared plus 1 is an even function. From the graph, we can see that too, like the area on the left equals the area on the right, or it has symmetry with respect to the y-axis. And the lower limit, upper limit, negative 2, positive 2. This way is convenient to rewrite it as twice of a half of the area. So we can rewrite this as twice of a half of the area, which is from 0 to 2 of the same function, because we use the even function property to work on this change from negative 2 to 2, just 0 to 2 and multiply by 2. And at the same time divided by 2 minus negative 2 or divided by 4 or multiply by 1 over 4. Now, when we simplify more and more using the properties that we know, the problem gets less complicated. 2 and 4 reduce, and then next step, you just find the antiderivative of the x squared and 1, and outside is still 1/2, right? Still 1/2. So x squared, use the power rule, but backwards. Remember, antiderivative is what is the function originally that you find the derivative to give you x squared. So we have x to the third over 3 plus x and evaluate from 0 to 2. And then replace the number, use the upper limit for the first calculation. So going to be 2 to the third over 3 plus 2, this quantity from the the replacing x with the value 2 or the upper limit subtracted by 0 to the third over 3 plus 0, which 0, that's convenient. Now we get in a number 2 to the third, um 2 to the third, which is the 8 over, let me see what I miss here. We have 8 over 3 plus 2, and then multiply by 2. Okay, and we get the number like 7 over 3 as a result. 7 over 3, and the value is 2.3 repeating. 2.3 repeating. This is the average function value or the f bar, and from the graph, that means the point on the y-axis here, or the average function value f bar, is 2.3 repeating. That is the value somewhere between the lowest y and the up and the highest y, or the minimum y, between minimum y and maximum y. If we use the f bar and then multiply by the width, we're gonna get the same as the value of the definite integral, which is the net area. The second example, we find the average value, key term again, average value for the following functions, and draw the graph if we want. Okay, if at the end. So for this example, f of x equals e to the power 2x, and the point from 0 to natural log 2. For the graph, the exponential graph, may be easier to sketch the graph at the beginning to see what's going on. From 0 to natural log 2, the exponential is the increasing graph because the base is greater than 1. Okay, I just sketch it. At 0, the function value is 1. And at natural log 2, let's see, e 2 times natural log, yeah, e 2 times natural log of 2 is e to the natural log 2 square, which is 4, and comes up to be 4. Get the value here 4. And based on this net area, we can use it to find the average function height or the function value. The f bar gonna be somewhere between 1 and 4. Okay. Now to work on this one, find the f bar, which is 1 over the width or the b minus a or natural log 2 minus 0 multiplied by the definite integral from 0 to the natural log 2 of the function e to the power 2x with respect to x. For the e to the 2x, the antiderivative is e to the 2x. Remember backward chain rule? So we divided by 2 because on the if you are not sure, when we find the derivative of 1/2 e to the 2x, using the chain rule, we will get back to e to the power 2x. Okay. From the antiderivative, now we're gonna replace the value 0, value natural log 2 to get the answer. So 1 over natural log 2. The first part, we see the divided by 2 for our convenience. I'm gonna make 2 outside of the grouping symbol. So to make the problem cleaner as e to the 2x, and I'm gonna evaluate from 0 to the natural log of 2. So at least, my working area here, when I substitute the number, is not too crazy. So we have 1 over 2 natural log 2 multiplied by the first round, we replace the x with the natural log 2 quantity. The second round, we replace x with the value 0. And this is the point that I mentioned earlier. When you replace x with the 0, it doesn't mean that quantity will go to 0. This case, e to the power 0 is 1. And the second part here, the first part from using the upper limit as we calculated earlier, that is the value 4. Okay, so 4 minus 1, we get the average function value f bar equals 4 minus 1, which is 3. So we have the number 3 divided by 2 times natural log 2. Okay, that's the exact value. If we look for the real number, in the decimal form, we would get the value 2.16. So it's about 2.16. So that means 2.16. That's the proof from the picture that we drew earlier too. So the height 2.16 somewhere over there, that would give us the area of this rectangle the same as the net area of the original function e to the power 2x from 0 to natural log 2. So this is the answer.